Right, let's kick off. Hello, everybody. My name is Phil Archer. I work for W3C, and it's my great pleasure to welcome you to this webinar today. It's not quite the end of the Big Data Europe project. We've still got another 6 months to run to disseminate the results and maybe look at more implementations and stuff like that. But today does mark a very important milestone in the project, which began in January 2015, so we're 2.5 years in now. And as we'll be hearing throughout the next 90 minutes, the project has developed something that I think is quite remarkable, taken a lot of existing bits of big data technology and put them together in a novel way, which it's true to say when the project proposal was being written, if you're involved in this kind of work, you'll know that proposals get written ages before you actually start the work. It's a good 3 years since we were writing the proposal. At that time, a lot of the technologies that we're talking about now and using simply didn't exist. They've come along since then, and yet they're incorporated in this remarkable platform that we're going to hear about today. The project as a whole not only is about the technology and about providing tools, it's also about doing something practical and meeting the 7 societal challenges that the European Commission has identified. And we'll be hearing about 2 of those towards the end of the webinar today. I want to encourage you throughout the proceedings. As you'll see on the screen, we really want you to ask questions. As you hear people speaking, please jot the questions down in the question box. You should see that somewhere on your GoToWebinar panel. I will see those and I will moderate those right at the very end. In a nutshell, as you'll be hearing, Big Data Europe Integrator platform tackles not just 1, not just 2, but all 3 of the V's of big data. It handles the velocity issue, it handles the volume issue, something we're particularly proud of. It really does handle the variety problem that comes up with big data as well. And of course it does that using wonderful W3C semantic web technology. We'll come on to that later on in the proceedings. My job today is very simple. I simply introduce people and then take your questions at the end, and so you won't hear from me in between times. So I'd like now to hand over to one of the lead developers of the Big Data Europe Integrator platform, Hajira Jabin, who's been instrumental in designing and executing this project, and she has a lot to tell you about the way it's been done and the excellence that's available, and she'll tell you all about it. So Hajira, I will hand over to you now and speak to you again later. Thank you.
Thanks, Phil, and good afternoon, everyone. I'm Hajra from University of Bonn, and today we are very excited and happy to announce our public platform release. Together with InfAI and TenForce, we've been working on development of the architecture and implementation of the architectural design of Big Data in Europe platform. So the platform was developed by keeping in mind some main targets. The main target was to lower the barrier of getting started with the big data platforms and technologies that are prevalent nowadays. We wanted to make it as easy to use as possible. We also wanted to make it open source. We wanted the platform to be flexible, to be able to support a variety of use cases for different 7 societal challenges, as Phil has mentioned already. Because the big data landscape is changing very frequently, so we also wanted the platform to be able to embrace emerging big data technologies, and we also wanted to make sure that there should be some integration possible between custom components into the platform. As you might have seen this big data platform picture before, it tries to give you an overview that there are numerous different tools available, and new tools are being added every day to the big data platform. All of them serve one or the other specific purpose in big data value chain. So it's not straightforward to be able to integrate most, if not all of them. So I will go through the evolution of big data platform architecture that we developed during the course of this project. Initially, we decided to use Mesos as a distributed kernel, And on top of this Mesos, there would be frameworks like Docker Swarm, Marathon, and Kronos. The main idea behind this architecture was that we thought that there would be some applications natively installed on the architecture, and some of them would be provided as Docker container components. But later, with the evolution of Docker Swarm and Docker Compose also matured, we realized that this is not needed anymore. So we deprecated this architecture and we simplified our architecture, which looks something like this now. So here we are using Docker Swarm as the resource manager and as a cluster orchestrator for Dockers. Docker is actually a lightweight visualization tool which allows you to wrap a software application along with its dependencies in a single software platform. It makes sure that your application runs as intended regardless of the underlying platform or hosting environment. Docker Compose is another tool which allows you to create multiple Docker containers simultaneously using one command and writing a script in one dockercompose.yaml file. So although this architecture looks quite simple and easy to use, however, there were some limitations or gaps in this existing software. The prominent being not able to create a workflow of different running applications. So for this reason, and to introduce easy to use interfaces, we introduced a support layer. In this support layer, we introduce a microservice that is named init daemon. It allows you to create workflows of different running applications. By workflow, we mean that it might happen that certain applications depend on each other in a running pipeline. For example, a Spark applications might need to read data from HDFS cluster, and Spark worker needs Spark master to be up and running before they try to connect to the master. So these workflows or the dependencies of different Docker containers need to be written somewhere, and we needed to make sure that required container is up and running before the connecting container tries to connect to it. So init daemon microservice solved this issue. Another limitation was that most of the big data components, they have their own web user interfaces available at different URIs. And of course, they are developed by different vendors, so they have different look and feel with them. So it's a bit cumbersome to navigate through different interfaces available at different URIs. So what we did was we created an integrator user interface that allows you to navigate through different web interfaces of running pipeline components in a one URI and in a homogenized fashion. In addition to that, there are many other user interface components. I will come to those components later. So another nice feature about this support layer is that this support layer itself is a Docker component. So you can easily opt out of it if you don't want to create workflows or if you don't need user interfaces offered by Big Data in your platform. You can easily not install them. In addition to the support layer, we have also worked on semantic big data. This is actually related to heterogeneity of the data. During our work with 7 societal challenges, we realized that most of the societal challenges need to deal with heterogeneous data coming from different sources, and we need to integrate that data somehow to be able to in order to be able to perform meaningful analysis on that data. And for that reason, we have two nice features added to Big Data in Europe platform. The names are Sansa and Ontario. That will be detailed later in this presentation. So this is an alternate view of our platform architecture. Here you could see that resource manager is the Docker Swarm, and top of this you could have a data layer that could contain one of the numerous data stores like Hadoop, HDFS, RDF store, or NoSQL stores like Elasticsearch, Cassandra, and so on. In platform layer, you could have Spark, Flink, Kafka, or Flume. And in semantic layer, we offer Ontario, Sansa, and Simangro. Then support layer is what allows you to create these underlying layers in an easy to use manner. And in app layer, a user would write their own analytics algorithm to be able to work with the data stored in the data layer and platforms in the platform layer. BDE supports a variety of different frameworks for different purposes. For example, for searching, we offer Apache Solr. For data acquisition, there's Apache Flume. For message passing, we have Kafka. For data storage, we have multiple different tools. For data processing, we have created Spark and Flink Docker containers, and for different semantic components. So the important features that BDE platform offers is a development environment that includes a stack builder, workflow builder, and instructions to add custom components to the BDE stack. And then there is an administrator interface that includes SwarmUI. And then we have an integrator web interface that we call user interface, and it also allows you to monitor the workflow of the running pipeline. So in order to get started with big data in Europe or get started with these tools that we have created, BDE provides platform installation instructions and usage instructions, how to create a stack, how to create a workflow, how to monitor the stack, and how to integrate different components in the platform. Installation guides can be found on GitHub Wiki pages, and also there are accompanying screencasts that you can find on our Big Data in Europe YouTube channel. A stack is essentially a collection of communicating components that solve a specific problem in the data value chain. So a stack is essentially described in a Docker Compose file. So it has component configuration and application topology. So you can download our stack builder from the GitHub page, and it allows you to select components from Big Data in Europe GitHub repository to create such a stack. Then there is a pipeline builder that allows you to create workflow of the components that you have already selected from the stack builder. And then workflow monitor allows you to monitor the workflow. If HDFS has started, if HDFS is running now, can Spark worker try to connect to Spark master now? So you can see status of different running applications at a specific time. Then we have also provided comprehensive instructions on how to integrate custom components in the Big Data in Europe platform. These components essentially need the microservice init daemon, so there are comprehensive methods and with some examples to tell you how to integrate init daemon in your own components. So it's essentially related to how to integrate custom component. In user interface integration, we also provide comprehensive instructions if the component has its own web interface, then how to adapt the CSS files necessary to give it the same look and feel and to be able to integrate in the integrator user interface. So as I've already talked about, Big Data in Europe platform offers numerous user interfaces to facilitate the use of the platform and to facilitate the use of the big data tools and frameworks. So here we offer workflow user interfaces, workflow builder, monitor, and then Swarm user interface to monitor the status of individual running containers to scale them up or scale them down. And then there is integrator user interface. So details will come in the following presentations. Now Ivan will show you a running pipeline example. So forward to you, Ivan.
Just a quick reminder while Ivana gets himself set up, do please put your questions in the question box. We'll come to those at the end. I've jotted down a few, but it's always better if they come from people joining us for the first time than me. So do please feel free to put questions in the box there, and I will get to them later. Thank you.
Hello everyone, Ivan Milov is here from BDI, and I'm going to talk a bit in more details about the architecture of BDI Integrator platform.
Ivan, can you get a bit closer to the mic? Sorry, I can hear you, but it's very faint.
All right, one moment. Is it better now?
Much, thank you, yes.
All right, so I'm going to talk about the architecture in a bit more details. So what Hadra already mentioned, we have an architecture which looks like this right now. This is actually architecture deployed in NCSR and in Phi clusters. Basically, we deploy Docker Swarm on the physical nodes, and on top of that, we deploy the BDI Integrator platform, which consists of components bundled in a custom way, which solve problems of particular pilots, basically. What is important to notice here is that we have a support layer which performs different tasks like integrating the user interfaces together, and which supports deploying the pilots in different ways. So I'm going to go into more details into that. So I want to emphasize one more time that the platform goals are to ease the access to big data technologies for wide audience, and also the integration of the custom components should be simplified. With the architecture and with the support components, we aim for 4 categories of the users here. It's developers, DevOps, big data experts, and cluster administrators. And essentially, we had 4 tasks in mind. The first one is setup of the platform, which was covered previously. You can do it manually, or you can use Ansible scripts to deploy it. There is development covered by support of Spark and Flink application templates, and you can deploy as a DevOps, you can deploy the whole pipeline using Docker Compose files on a Docker Swarm, and the monitoring is enabled using the Elk stack. So essentially, while developing these components, we envisioned the BDI Components Lifecycle, which consists of these 5 steps. The first one is development. When you take the particular big data component and you develop it, it could be a Spark application or Flink application, and this is supported by the application templates. Then there is a packaging step where you basically pack everything into Docker file. After that, there is a composition step when you take several of those Docker files and put them together inside Docker Compose definition to deploy it on the server. After that, there is an enhancement step, which is basically taking support components and enhancing Docker Compose files so that you will have integrated user interfaces and init daemon and all this cool stuff inside. After that, we could deploy it with Docker Compose, and the last step is monitoring, and it goes back to the development, basically. So I'm going to go through some of those blobs. The first one is development. There was a blog post on our WordPress. You can take a look at that in more details. Unfortunately, I don't have much time to cover it here. The basic idea that you can deploy a simple Spark cluster using one Docker Compose command, and you can see it here. I output a make file. Basically, the target's called Spark. It will deploy the Spark cluster, and then there is a Spark app target which builds and runs the Spark application. I will show it later in the demo at the end of my talk. UI Integrator application, one solution which we needed to integrate interfaces is basically taking all of the web interfaces you have inside the BDI stack and put them together. Right. Then the CSS wrapper. This is a component which injects the CSS inside the inside the other components, so we could modify the CSS to reflect the style we have inside Big Data Europe platform. So all of those components got full blog posts on our website. Please go ahead and read those. So I will proceed to demo. It will take around 8 minutes. I need a moment to redirect my sound. Hello everyone, this is a companion video for the release of the BDI Integrator platform, and I'm going to show you how to deploy the platform, and I'm going to show you it on an example of actual setup we have an N5, which includes 3 physical hosts, NC4, NC5, and NC6. And the setup itself will include the Hadoop cluster name node with 3 data nodes distributed across those physical nodes, Spark with 3 Spark workers, UI integrator. They're going to be a reverse proxy with CSS wrapper, and HDFS file browser, nice interface to upload our files to HDFS. So the whole setup thing is available on our GitHub, and you can just go there and take a look if you're interested after the presentation. Right, so let's get to it. First of all, I'm on the XW NC4 server, which runs Docker Swarm, and I'm showing you that I have indeed 3 nodes here with these URIs and these host names. So what I'm going to do is I'm going to first deploy the cluster, and I created a make file for myself here. What basically does, it creates an overlay network first, which is called BDI demo. Then it's going to build Docker Compose file, because I have to build Integrator UI to include the interfaces in there so I can navigate through them. And then it's going to just make it up. So let's go quickly through the Docker Compose YAML file to see what's in there. There is basically UI Integrator, which is going to be available on demo.bdi.org, and this is the main interface we're interested in. There is a CSS wrapper, which is reverse proxy. This is a modification of J. Wilder and Nginx proxy, which is going to listen to the Swarm master and basically proxy all the interfaces which export as a virtual host to the outside world. There is one name node which got cluster name test and a bunch of other configuration parameters, and it's going to be exposed to name node.bd.xl.org. We also like here the modification for the JWilder proxy, which inject the CSS source during the proxying basically. There are 3 data nodes. Also what you can see here is Spark master, and it exposed on sparkmaster.bd.xl.org. And what is important, there are constraints, and I want to deploy Spark master and the name node on XW4, and 3 data nodes should be deployed on each of the physical nodes, and the same goes for Spark workers. I have depends on clauses, and depends is got a condition service healthy. I got health checks on all those services, and that means that Spark master will not start until name node and at least one data node I just chosen data node 1 is healthy. The same goes for Spark worker 1. It will wait until the Spark master is healthy, and then we'll start. So at the end, we got Hue, which is a bit modified because we're only interested in the file browser here to copy the files there. I included the health check here as an example directly into Docker Compose file. Basically what it does, it just pings localhost on port 8088, and whenever it returns 0 code, it marks it as healthy, and there is a dependency on top of the file, then the CSS wrapper can start, because it waits for all the services which we exposed to be healthy. So let's start it. Do makeup. Now our cluster is up, And what you can do is you can do docker compose -h this port, and then you do ps, and you can see that all of the services are indeed running. So what I'm going to do, I'm going to go to browser, and I'm going to go to demo, and here it is. So I click on name nodes, I can go to the name data node tab, and I can see that indeed 3 data nodes are running. The same goes for Spark Master. I can see that 3 workers are running and they are live. And I can go to the HDFS and I can actually log in. I logged in into HDFS, and what I can do right now is I'm going to upload a file. So I will have it later as an example for the application I'm going to run on this cluster. So what I'm going to do is I'm going to upload this book.txt file, which is Lewis Carroll Alice in Wonderland. And right now I'm going to go back to the terminal, and I'm going to first run a simple Pi calculation on this cluster, which contains in a Pi YAML file. So you can see here that basically I set up the Spark Master to be Spark Master. Because it's in the same network, it's going to see it by this host name, and the host name is basically the name of the service in Docker Compose definition. The port is the default one, I didn't change this one. This is copied inside the example app Docker Compose. So if I go to see this thing, you can see that I'm copying Spark examples to the app. So this points directly to the jar file, and it points to the main class which is going to be executed. I got this command to run it inside makefile, and it builds it and then runs it. You can see some output, Spark magic is happening, and then you can see the Pi estimation here. So the next thing is I have to modify the word count, the next sample application I'm going to run, and I have to point it to the exactly book.txt where it is located. Let me take a look. And it is located in the correct directory, so actually I don't have to modify anything here. I'm going to run the second example. It's again going to build it, then going to run it, and all right, you got really long output with a lot of words counted inside the Lewis Carroll Alice in Wonderland book. And that basically concludes this demonstration. The cluster is going to be available online. I'm not going to share the login and password for you because of security reasons. However, you can navigate there and take a look that it is indeed running and it's deployed with integrated nice interface. There are several things to simplify this setup, and this is going to be covered in the next presentation. Thank you for watching.
Okay. Thank you very much indeed, Ivan. Hajira, I think is it back to you now?
No, it's Art now. Art will present the user interfaces, and they're working now.
Thank you. Thanks, Art.
So up to you, Art.
Just a reminder, please do post your questions.
Right. Thank you, Phil. Thank you, Nora. Thank you, Hajira, sorry. I'm here with Nora Sepesh, and we're talking about the user interface for a moment. So it'll be, well, I suppose a bit more lightweight than the earlier presentation, so we can relax for a second. When we're looking at the user interfaces, there's a few things that we are interested in. We're looking at interfaces that are helping users in the same way as Ivan presented nicely earlier on. There's a setup phase that we want to make simple, but that's already covered by the Docker system. There's the development itself, and we'll talk a bit about that with the templates, as Ivan also showed. There's a deployment system where we can show some nicer interfaces for, and then there's the monitoring. That's the thing that I'll go into first. In terms of monitoring, there's not really anything you can do that works automatically out of the box and that always works for any component that you want to run. There's always some kind of custom thing in between. Something you can do that will somewhat always work, at least if you're on Linux machines or server systems, it's just monitoring standard output. And of course we do that, and I'll show it in a second. That's one of the things we can do, but it's not always the nicest thing to see. On the total other side of the spectrum, you have dedicated user interfaces. That essentially means that you make specific applications to monitor things. For instance, something to monitor your Spark master. It's also something that Ivan has shown, and it's also something we'll dive into. You can make more of these and you can play a bit with them. Other things that you can do that are semi-generic are monitoring the wire format. For instance, we monitor the HTTP traffic that goes on in your cluster if you want, and you can log that sort of output. Or you can look at the status of a stack, being which elements are currently running and how many of those nodes are active. Let's go into that first for a second. So if we go back to the concept of just standard output logging, that gives us something like this. This is a Spark master, and this is the output that it generates. It's a whole bunch of text, essentially, of it telling us all sorts of things that, when you're a developer, can be quite interesting, but only when it's broken. In the end, what you see is that the master says there's a worker here, and that's also something we'll see just in a second from now. Let's go dive into the custom user interfaces, as they're, well, different and more lively. If we go to the Spark master, this is one process that is running, and it has, as Ivan already showed earlier, a bunch of stuff running in it. It's a different project though. Here we see a Spark master, and the Spark master says that there is a worker, and the worker has 3 cores, as we could see earlier, and has a certain set of memory available. You can also go to the Spark worker, and you can see a bunch of things that are interesting to see. There's also the visualization, for instance, which is a completely custom view of something that is running. I'll go into it for a second. In a second, I'll first go into the monitor. The monitor is the visualization of the init daemon, essentially. And what this essentially does, or what it means, is you'll see that your process has a set of steps. So your big data pipeline, everything is packaged into it in that single Docker Compose. And as everything is packaged in that single Docker Compose, everything boots up at the same time. So that means we start calculating everything before we've uploaded our data. That's ridiculous. Of course it's ridiculous. So what we do is we manage that setup a bit, and we do that using the init daemon. Now you might think in yourself, I followed the Docker community and I know the Docker health checks are currently something that is more common, and Ivan has shown them, so you can assume, yes, they work. Of course they work. They integrate now with this init daemon, and you have the best of both worlds, in which we still support you in your old way of working with the init daemon and gradually move you towards the health checks. Health checks are slightly less expressive, say. What we have here is we see a few steps. The first thing that happens is setup of HDFS. It means that we're setting up our file system. Next we set up Spark. Then we require users to upload data. That has happened. And now an aggregate data run loop is running. That run loop will keep running until, well, we stop this whole thing. We have this custom visualization. If you go to the complete other end of the spectrum and want to visualize something completely dedicated, specific for your use case, specific for rendering output of the pipeline you've just built. It's very expensive to build, of course, because it only works for that pipeline, but you can integrate it in one nice and integrated user interface. And that is essentially what we want to go to. When you receive this application, you have enough means to monitor what is going on, to see what is going on, and to have a sense of control over this whole thing. As we mentioned earlier, we have this dedicated user interfaces. We have the standard out. We also have the wire format that we can render. As you can see here, we monitor the HTTP requests and we convert them and we figure out what is going on with them, and we throw them into Kibana after they have been parsed. Now, Kibana is just a common tool that you can use in order to render all sorts of visualizations. Common visualizations you can show that already exist, like the response status. Of course, you need to select what time frame we're looking at. Let's pick 12 hours, that always works. And you can see a few of the outputs that are are given here. So apparently most of our responses have been 200, some are 500, and some are 302. You can do more with this. You can build your own custom dashboards if you need them with some basic or more complex information. This is one that we generate and that we can use now. It shows a few interesting things like the response body size versus the amount of time it took to render them, or the total amount of queries that were made, and some other more complex statistics that we can use. Right. What you actually get out of Kibana, that heavily depends on what you do with it. There's many good tutorials on Kibana. It's a complex thing, but you can get a lot of information from it. The good thing from this portion of the component is it just runs. So that means that you can run this within your pipeline and you don't need that much extra configuration as you would with some custom deployment system like or visualization system like we saw earlier. Let's go back to the SwarmUI. The SwarmUI shows you your SACS status essentially. So we looked at this to look at the standard output. But what this actually shows you is it shows you all of the components that are running. So for instance, there's an integrated UI, a node manager, and there's here the Spark master, there's a Spark worker in here, all sorts of stuff. You can look at the logs from this point, but you can also scale things up. So if you notice that a certain process takes a lot of time, you can ask it to use, for instance, 3 identifiers rather than just 1. And it's very easy to scale up and to come back and see what is going on with the system. Of course, we're always looking at things we can extend to this regard, but in its hard core, this is the useful thing here. We see now how we can use this in order to monitor our system, but there's of course more to be done than just the monitoring. If we quickly go back, then there's also the development that we would need to do at some point. In terms of development, we have built the workflow builder. I'll go into it in a second and you'll see it. The SwarmUI, which you've just seen, but you can also use that to deploy new pipelines after you've built them. And the stack builder, which will actually help you compose applications. Let's go to the workflow builder first. The workflow builder, you've seen here that we can monitor our application. And if we monitor our application, there's this set of steps that need to occur. At some point, you'll need to configure this set of steps. Whether you want to do it in a text file or you want to do it somewhat visually, many people would like it visually, and we've supported that. So in the workflow builder, say that we have an application for analyzing the barcodes. There's a certain set of steps here that we've already predefined. For instance, one is that we start AGFS, then we start the Spark master, we set up the Spark worker, we upload some data, we run our calculations, we extract the calculations, and we'll automatically disseminate things. Each of these steps, should they not be in a logical order, you can reorder them. So it's very easy to change things around and to have a normal understanding of what is going on. It's also very easy to publish external things of this or to add extra steps. For instance, it might be that we need to upload extra data. Then we can just write that here and create a manual step for that. Extra data. We can add this and we can order this so that it's at the right position. All right. Apparently dragging. All right. Looks like this. Awesome. Very easy to use, and there's, it gives you a nicer visual feedback of the thing that you are doing there. Next up was a SwarmUI. The SwarmUI, we walked through it a few times, and that's common because as you walk through it, as you notice and you use user interfaces, you notice that some user interfaces are useful for more than one user. The SwarmUI is certainly a central component. It allows you to run new things. Okay, so how do we run new things? Well, essentially, if you want to create a new application or want to share a new application, what you do is you go to a place that a developer gives you. He'll give you probably this GitHub URL or any other Git URL as long as it's public. And you can create a new source for that. This is WebCat, for instance. You clone that URL, you paste it in there, and you press create. Once you press create, it will be added to the pipelines here below in a few seconds. No, sorry. You have to launch it. You launch it, then after a few seconds, it's added here below, and you can monitor it and change it in the exact same way as you would normally do. Right now, this pipeline is not running, but if you start it, it'll automatically start up and do everything that the others do. as a last thing, there is a stack builder. So we've seen these components, and as you've noticed maybe, you need to figure out what things you need to combine. If you look at the location aggregator, for instance, there's quite a few components here, and it can be daunting to select the right technology so that they can work together. And although, you know, it's always easy to make these things better, it's a continuous work that you have to do. And we're working on this currently as a stack builder, and the first release is there. You can use a stack builder to define new stacks to develop new things that you want to run together. You can create a new Docker Compose file, for instance, say that we want to do something with Spark and Python. You can just search here for, say that we want to do something with Spark. We can search here, and what it'll do is it'll search through our BDI GitHub places, or at least something we aggregated from there on. And what you can easily do from here on is just figure out what's here. And there's multiple things. So there's a Spark base that we might be able to use. There's also Spark Python. And with Spark Python, we see that there's 3 things in there. There's a master, worker, and a Python template. And you can just drag and drop that here, and it's in your Docker Compose. And you know that these things of Spark will work together. The same thing we can do for AGFS, for instance. We can see AGFS. There's apparently 6 components for AGFS. Drag and drop it on there, and it works. What you may notice now is that your Spark worker needs to depend on AGFS being up. So if I go here, I can write something like Hadoop, and it'll give me hints on the other names that are here. So I'm kind of being guided through the process of figuring out what needs to work with together with what and how it will work together. So it's a very, very simple way of managing this whole thing. From here on, you can, of course, save it, you can download it, you can publish it on a GitHub. These are our user interfaces, and they're very much down to earth in ways in which we help you. They're always still governed and figured out towards how can we help that end user. Other things that we, of course, can do with this is a more researchy position, and this is where I think we should give the word to Jens Lehmann that will explain a lot of these things. Phil, it's up to you.
Thanks, Ad. Very lively as always. Thank you. Jens, I will hand over to you, and you can talk about how, as I say, as I mentioned right at the very start, one of the things we're very proud of in the Big Data Europe project is, as you've seen there from what Ad was just showing you, the extraordinary amount of power there to link different things together. They generally handle the velocity and the volume aspects, but variety is always the big problem with big data. How do you take multiple sources of data from in all sorts of formats and so on? Big Data Europe is very good at handling that, as Professor Jens Lehmann will now explain.
Yeah, thanks for handing over, Phil. So can you hear me well?
Yep, no problem.
Phil, can you hear me well? Okay.
No problem, yes.
As Phil just said, in a lot of the challenges we encountered, variety plays an important role. So we developed together some features of the Big Data Europe platform which address this in particular. And those are 2 projects I want to present here. First, the SANSA project, and then the Ontario project, which are both integrated into the Big Data Europe platform. So I'll first start off with SANSA. So the main motivation behind SANSA is that a lot of the data we have to deal with is in graph structured format. So I guess a lot of you know the Google Knowledge Graph, for instance, the Wikipedia Knowledge Graph derived from Wikipedia, but also a lot of the data we had to deal with in the societal challenges in the Big Data Europe project, as well as social graphs. But at the moment, there's only limited support for scalable querying, inference, and machine learning over this data. So that's exactly what SANSA is targeting. To realize this, we basically combine 2 different worlds. So on the one hand side, we have distributed analytics frameworks, which you will just see in a second, where you have in-memory computing frameworks like Spark and Flink and their machine learning libraries. And on the other side, we have the Semantic technologies stack, where you have standards like RDF, the resource description framework, Sparkle, which is a query language for RDF, as well as ontology languages like RDFS and OWL, which allow to describe a domain and the terms in it. And we combine both worlds into the SANSA stack. And the main idea behind it is that we can combine the advantages of both. So the semantic web stack is very good for handling this variety dimension. So you can integrate data easily. You can do expressive modeling if you need it, and you can draw on W3C standardized formats, which is very useful because you will probably end up spending less time in your data preparation and processing steps. And on the other side, we combine this with scalable technologies from frameworks like Spark and Flink. So by doing this, we end up with the Sansa stack, which you can see on the right side here on the slide. It's essentially a framework for distributed RDF dataset processing, which aims at high scalability and fault tolerance, and it consists of several libraries, which I will just go through here sequentially. We start off from the lowest layer, or the lowest layer which works on top of Spark and Flink. That's the knowledge distribution and representation layer. So there we have functionality which allows to read in RDF and OWL, which is the ontology language we support in different formats, and represent them using, for instance, RDDs, which are common in Spark, or data frames, graphics, or as a tensor representation. And also allows, or there's early support for allowing to transform between those different formats. So each of those formats are suitable for different analytics operations which you can later perform. And essentially this library provides several convenience methods to read RDF and OWL data into those formats. You can also already calculate several statistics on your data set. So there we have a lot of out-of-the-box functionality which is provided. So that's the lowest layer. On top of that we have a query layer. After loading the data, you of course want to query it. So we at the moment mostly rely on the Sparkle query language, which is again a W3C standard, and developed some intelligent indexing and splitting strategies. We also include some research from external projects here. For instance, we use virtual views over different data sets to efficiently combine and query them. In the next step, what we are currently doing is that we evaluate those query engines, and we'll find out which of them is most suitable in which context. And Sansa already provides a Sparkle compliant endpoint. So when you read in the data set, you have basically distributed triple store. So on top of the query layer, you have inference, which means you can draw conclusions from the data you have. So for inference, we draw on a lot of research work which has been done already before, but the distinguishing feature of Sansa is that it can build a so-called rule dependency graph dynamically. So you have different profiles for the language you want to use for inference, and in each of those profiles you need to have so-called dependency graphs which determine the execution plan, and that's something which is done very intelligently within the project, and it essentially allows you to adjust your performance levels. You can basically include as much inference rules as you need for your project and see how efficient you can execute them. So that's for the inference layer, and the largest layer is the machine learning layer on top of those. So there we develop several machine learning algorithms which really make use of the graph structure of the underlying data. So that those are usually not just plain feature vector-based approaches, but approaches which reuse the semantics, the descriptions in the ontologies, and the graph structure of the data. So this, of course, I cannot explain in detail here in this short amount of time, but we have, for instance, algorithms for knowledge graph completion, which predict missing edges in the knowledge graph, for graph clustering, for rule mining from graphs. So-called semantic decision tree is currently developed, and we also are working on so-called knowledge graph embeddings, which are very similar to Word2Vec and other projects, in case you heard of those. So just to summarize this, so Sansa is a generic stack for linked data. So we build on top of distributed memory frameworks, in particular Spark and Flink. That's the project itself is very easy to use. You can just add the dependencies to your existing Spark or Flink project. So that's very easy if you use, for instance, Maven. And we support a lot of functionality for querying, inference, and machine learning. The 0.1 release was done in last December, and then we do releases every 6 months, so the next one will be in June then. So that's for the Sansa project. So the second project, which also targets the variety dimension, but from a slightly different, more high-level perspective, is Ontario, which realizes a so-called semantic data lake. So the motivation or the problem here is that in many cases you have to deal with those data lakes in companies. Often they are more data swamps than data lakes. So you store all the data you have there, no matter what format, and usually in HDFS. So there's usually no unified schema, and it can be difficult to organize all of this. So the idea of the semantic data lake is to add a layer on top of this, where you can semantically lift the different original data sources. So the sources essentially stay as they are, but you add a thin layer with semantic annotations on top. And then the idea is that you can have queries which range over several of those sources. So this works by first decomposing your input query into several subqueries, keeping the provenance information, so that the links between the subqueries. Then you check which candidate data source can answer the query, and each subquery is then translated to a query which works on the actual data source. So if your actual data source is a relational database, you would use SQL as query language and the Sparkle to SQL rewriter for realizing this. At the end, everything is joined together to form a result. So that's also visualized in this figure here. So on the top left, you have the incoming Sparkle query, which is then decomposed into several pieces. So you keep the metadata. From the metadata, you know which part of the query refers to which data source. So you go to this data source, then you know the type of the data source. You call the correct rewriter for this data source, which can then answer your query. And in the second stage shown here, you get the results from each of the sources. You do a reconciliation phase. So in this phase, you need to know how to combine the subqueries, but we have this data from the original execution plan, where we kept the links between the subqueries, and you compute the final result. So Ontario, or the semantic data lake, essentially allows you to have a thin semantic layer on top of all your data sources and enables querying across many different data sources, which helps you, of course, to structure your data. So that's it from my side. So we have those two variety projects, Sansa and Ontario, and I think they can be useful in a number of contexts. So I think I hand over now to the next presenter, or to Phil first.
That's all right. Thank you, Jens. I'll pick up the baton and hand it back to Hajira, who's going to summarize what we've heard so far. While we do that, thank you to the people who have entered some questions, and we'll come to those shortly. But I just wanted to pick up on one already. Emmanuel, thank you for your questions about Copernicus and Earth observation data. Yes, we are using that in one of the pilots. Frustratingly for you, that's not one of the ones we're about to talk about, but yes, and we certainly plan to do more of that in future. So yes, it's certainly a very interesting use case. Hajira, thank you.
Yeah, thanks, Phil, and thank you, Jens, Art, and Ivan, for a comprehensive overview of Big Data in Europe platform. So in summary, the platform is flexible, and it works based on microservices architecture, and it supports a lot of use cases that we will discuss in the form of different societal challenges. So now I will quickly go through the societal challenges. So there are 7 societal challenges which are acting as pilot showcases for the Big Data in Europe platform, and their specific data value chains are in execution on the Big Data in Europe platform. So these are related to different areas like health, food, energy, transport, climate, social sciences, and okay, for food for For health, this is the OpenFacts discovery platform related to biological, medical, and pharmaceutical data. And the use case is about querying this data to get answers to complex related questions. For food, it's about discovery and linking of viticulture relevant information, and there are different frameworks being used like Plume, HDFS, Spark, Kafka, and graph databases. For energy, there is system monitoring in energy production units, and it's using Kafka, Spark, HDFS, Postgres. For transport, it's about short-term traffic flow forecasting, so you get traffic forecast data, and the topics are created in Kafka, then Spark and Flink is being used for analytics. Then data is being stored in Postgres, Elasticsearch, and HDFS. So the climate societal challenge use case is about supporting data-intensive climate research, and they're using scikit-learn and TensorFlow, and for storage they're using HDFS and Postgres. Sixth societal challenge is about social sciences, and where we are dealing with municipal data related to citizens and researchers' budget. And there we are using Plume, Kafka, Spark, HDFS, and Forstore. SE7 is about security, and it's related to ingestion of remote sensing images and social sensing data to detect and verify changes on the Earth's surface for security applications. And it is using Spark, HDFS, Lucene, Cassandra, Straben, Simagro, Postgres, and many others. So the main purpose of having these 7 different societal challenges and having 7 different showcases is to show that these kind of data value chains or these kind of workflows are capable to be run on Big Data in Europe platform that is being developed within the course of this project. On another abstraction level, if we compare Big Data in Europe to the existing platforms and tools, we could see that Big Data in Europe also supports HDFS as a file system. On the other hand, it does not have a native installation. It's a lightweight visualization tool. It also has a flexible modular architecture, which is different from the other existing distributions. BDI also offers high availability. It is free to use. It has nice scaling capabilities as offered by Docker Swarm. And it makes it easier, and it makes it possible to add custom components to the existing platform. Another nicer feature is that it is able to work on any native host environment, that including Windows, Mac, and Linux, that are the most popular. And management tool is Docker SwarmUI and some custom interfaces that we have prepared within the course of this project. So in summary, BDE is not being built on top of existing distributions. It's a platform in itself, and it is targeting communities and research institutions to make it easier to get started with new tools and frameworks. We are trying to bridge the gap between scientists and open data, and there are also multi-tier research efforts towards smart data to cater for the heterogeneous data. Regarding maintenance of Big Data in Europe platform and update, it's community driven. You can find it on GitHub. There are some adapters from the industry. The names are Pyrga, Eurostat, and many others. And then we also have follow-up projects like Hobbit, Special, Big Ocean, Crowd, and many others that are using Big Data Europe platform as their basis for complex analytics and stream processing or geospatial data processing and so on. So to wrap up, the platform makes use of containerized components. It is for development and runtime facilities. It showcases components relate them to architecture, and it's a microservice-based architecture. So that is it from my side. Now we will go on to showcase the two of the societal challenges for related to traffic and one related to citizens and municipal levels. So I forward this to Phil again. Thank you very much.
Thanks, Ajira. I think you can see why everyone involved in the project is so proud of what's been going on. It's really exciting, and seeing those different adopters, and those people outside the project who've seen what's been going on and have adopted the technology themselves. So that's very encouraging. Luigi, I hope you're ready and standing by. You are now presenter. Again, just to remind you, thank you for those who have been entering questions. I will come to them. But let's hear about one of these specific, well, actually two of the specific societal challenges that we're looking at. In this case, Luigi Selmi from Fraunhofer is going to tell us about the work on mobility data in Thessaloniki. Luigi.
Thank you, Phil. So I'm going to present the pilot case, and so for the societal challenge number 4, smart, green, and integrated transport, it's a broad topic ranging from urban mobility, safety, logistic, transport system integration. In the SCC4 pilot, we have decided to build a pilot that can ingest streams of data with the spatial and temporal dimensions, process them, and store the result in order to enable monitoring and forecasting of the infrastructure and of the traffic flow. One of our project partners, CERT, from Greece, is managing a system that monitors the traffic flow in Thessaloniki using floating car data. That means GPS data sent from vehicles. We are using this data to showcase the pilot. So let's start with the context. That is, we want to handle this data in a scalable and fault-tolerant way. And for this use case, we have selected some of the components from the BDI platform. Because the fundamental idea is to use the components following the microservice architecture. That means we have data producer and data consumers. The data producer, in our case, gets the data from the real-time stream or from the historical data. Send the data to a Kafka topic, that is our message broker. And our consumer or many different consumers can read the data, process the data, and store the result in a database where other application, for example, a web application, can be used for doing data analysis or plotting the data in a map or providing different type of visualization. The architecture, as you can see, is based on different components. The basic components are Kafka for the message passing, and Flink for the processing of the data. And these components needs other components. For example, Kafka needs Zookeeper. Then for our specific case, what we want to do is to compute the number of vehicles in each road segment in the Thessaloniki road network, and the average speed within time windows of, for example, 5 minutes or 10 minutes or more, for both monitoring and even forecasting. Then we have used Kibana and Elasticsearch for as a storage, and Kibana for the visualization. But other use case can be for example, based on HDFS to save the result and then using some other application to further for further processment. So from the BDI platform, we can use all the components that we need and that are provided by the BDI framework, by the BDI platform. So in our case is Zookeeper, Kafka, and Flink. Then we have other components that are specific of the pilot. One is, for example, for doing the map matching. That means matching the location of the vehicles to a road segment, and so that we can compute the average speed in the road segment and the number of vehicles. So as you can see from these slides, at the end we should have a system that is distributed and built on top of Docker images. These Docker images are run using Docker Compose. That and the order of the services is organized using the init demo from the BDI platform. So once we have defined the order in which the service must start, for example, Zookeeper must start before Kafka, we can start all the components using the user interfaces of the BDI platform. And in our case, we start with Zookeeper and then we start Kafka. And when we start Kafka, we can also create the topic that will be used by the producer and the consumer in order to communicate and share and send the data from the producer to the consumer. In this slide, we cannot see the full stack of the services because it will be too small. But I want to say that there are also the full component is Zookeeper, then Kafka, then Flink, for which we set up a master and two worker, then a producer and a consumer that are job application for Flink. And then in our case, we have different type of sync. We had tested Elasticsearch and Hadoop HDFS. As you can see from this slide, the data can be uploaded from the local file system into the distributed file system, that is HDFS. In our case, we have our sample data from the historical data provided by CERT. And as we start Flink from the user interface, we can see that the producer and the consumer are uploaded to Flink, and they start, and so the producers start to read the data, transform the data from a text format to a binary format, that is Avro in our specific case. And the consumer that can read this format because it knows the schema of the data can start to use the data and compute the average speed and the number of vehicles after the map matching. At the end, we have at the end of the processment, we can visualize the data as we have seen at the beginning. and see what's going on the Thessaloniki road network. So for this webinar, we have built a short demo, and we have shown the how we use how the BDI platform is used in order to set up an application, from the selection of the components, their composition using Docker Compose, and the init demo in order to set the order of the services, and then the user interfaces from which we can have a look at all the components that are used in the pilot. So for further question, you can write a message on the webinar, and if you have more questions, I'm
Okay, thank you, Luigi. So we've seen, thank you very much indeed, we've seen the Big Data Europe Integrator platform used there to handle streaming data, live data that's handling the velocity via big data and doing interesting stuff with real-time traffic data in Thessaloniki, working with CERT and others. So that's one of the societal challenges. Number 4 on transport. Another one we're going to look at now, I should say that there are pilots for all 7 of the societal challenges, and all 7 of them, as Hajira showed in her summary talk, use different components and do different things with it. There are pages about each of those pilots on the Big Data Europe website. So just to pick one more example, I'm going to call on Jürgen Jagobitz from the Semantic Web Company in Vienna. Jürgen's going to tell us about work on Societal Challenge 6, which is the one about social sciences, to be telling us about looking at a very different subject altogether, spending or monitoring of spending cross-border. Jürgen.
Hi, my name is Jürgen from Semantic Web Company in Vienna. Phil just told you. I'm going to give you a short introduction into societal challenge number 6, which is dealing with economic data. To be more specific, we are making budget data comparable. We're doing this by harvesting heterogeneous formats from different, in the beginning, Greek municipalities. We are getting them mostly in CSV on a daily basis. And what we are doing here is create a stack based on the BDI platform to normalize and link those input formats, whatever they are, into RDF and link them together. Then we are doing calculations of financial ratios. This is done by an economic specialist who provides the transformation to make those numbers really comparable. And after that, we are doing visualization of the data. Visualization in this case is done using full-party graph search. You will see at least a screenshot later. To give you an overview of the architecture, it is open. We are having in the left upper corner, we are having data sources for various municipalities, and we are using Apache Flume for data acquisition. It depends. So if there are new municipalities joining this this project, we're simply adding another Flume agent, and data will be processed. We are storing raw data in HDFS to make it available for further use, and we are distributing the incoming files through Apache Kafka. Apache Kafka is configured to to send out messages in the form of the file name and the file contents as byte arrays. You will see it in a moment. Then we are using Spark as a processing tool for parallel triplification, and either Virtuoso or Forestore if the amount of data gets larger, to store the data, and then we are presenting the final results within a web app. We also have the whole data set for further analytics. So we're using Apache Flume, which is here for data ingestion. It's capable of collecting and moving large amounts of data. Such a Flume pipeline itself, internally inside Flume, connects sources and sinks together via channels. In our use case, we're using one of the many already available sources. We're using a spooling directory source, but this could be any Flume source that is available. We don't know how municipalities will in the future provide their data, so we are open for any form that data is handed over to us. We're then using a memory channel, you will see it in a moment, and then using two sinks, the HDFS sink and the Kafka sink, and this is basically the whole setup for Flume to be able to ingest already large amounts of data and distribute them. To make you aware of how easy it actually is to use the Big Data Europe platform, you see the complete Docker file for the Flume Docker image. We are just adding a Flume startup JSON, which is basically the startup command as a JSON structure, so it's easier maintainable, and the Flume setup, the Flume agent setup, which is a proprietary format for Apache Flume. It will define the sources, the channels, and the sinks. So you see both of them, both of these files here, and they are simply added to config, and as soon as the Docker image is started, the Docker base image for Apache Flume will use the Flume startup JSON to upload the agent configuration to Zookeeper if necessary, and run the agent. Here I give you an example of the Flume configurations source. You see the Flume HDFS sink is commented for debugging reasons. We are simply spooling a directory, and in this case, and budget data CSV files can simply be dumped there, and they will work their way through the whole pipeline. You see, we're using a channel, a memory channel in this case, and also using a Kafka sink. So there is no programming necessary. This is already available and just needs to be defined. Then we are distributing those messages in using Apache Kafka, which follows the producer-consumer paradigm, and the messages are grouped by topic. So we are defining one topic in our Flume agent setup. In SE6, Apache Flume is creating the topic, and the messages are created by Apache Flume. They contain a file name as a key and the file contents as a byte array. In our case, Spark will be the consumer. Here you see again, it's the same procedure as previously. You see the extension of the base Kafka image. You simply add the startup command as a JSON file with all your settings that are necessary. Sometimes Apache Kafka is exposing a lot of options, so in a productive environment you might want to take care of them. Now, as a third part, as you remember from the architecture, we are using Spark, which is well known for parallel computing, and in our case, it acts as a Kafka consumer. It works on the Kafka messages, which were created in the first place by Apache Flume. Again, they are containing the file name as a key and the file contents as a byte array. What we're doing next, we're using the service provider interface. Is a Java programming feature to have a registry of parsers for different municipalities. Municipalities, unless there is a whole process of legislation, won't be the same all over Europe. So you need to be able to, and you need to be open for different formats of any kind. We're doing this by introducing such a registry, which will be able to determine by the file name, which is sent by Kafka, which parser is the correct one. I here give you an example of the Spark job. You see it leads a couple of environmental variables which will be given in the Docker image or within the Spark, within the startup command from Docker Compose. You see all the code is completely in pilot SC6 cycle 1 and pilot SC6 cycle 2. So you can really use this as a very basic example of how to do document processing in the first place, or data processing in a more general sense. We're also creating inside the Spark job a streaming context to be able to stream Kafka messages in a constant way. You need all those environmental variables. The whole code, as I said before, can be used, can be looked at on our GitHub repository, and is a very good example to get you started with those core components. Now, you also see an example here on how to process actually Kafka messages inside the Spark job. You also see in line, I think it's 89, if you can read it, how to access our budget data parser registry, which will determine, as I said before, the correct parser for a given municipality. We are then here uploading the transformed RDF into a Virtuoso, and that's basically it. You're also you see an example of the budget parser. You can use this also as a template and adapt it to your needs, of course. You also see Virtuoso uploader, which is extremely efficient, making use of W3C's graph store protocol. This is a sample of the Docker image, which is for the Spark job. It simply extends one of the latest Spark submit versions that we distribute. You only have to give the environmental variables that your Spark job needs, and point it to the actual jar file with all its dependencies. Now, we of course need to put these things together. We're doing this inside a Docker Compose. I'm showing you a couple of steps here, not the whole one, and you could do it also with the stack builder. Now, this, as Luigi previously mentioned, also requires Zookeeper, first for Flume and for Apache Kafka as well. So we are running Zookeeper cluster in the first place, and then we're creating a Kafka cluster. You see, it depends on the Zookeeper. In our case, we don't have any special requirements for further setting up any kind of topic or something. So the normal Docker Swarm depends on is sufficient in our case. As you've seen in Ivan's presentation, we are also using constraints here to be able to determine which service is running on which server. So this is the setup for Flume, which depends on Zookeeper and Kafka. Upon startup, Flume will automatically create the Kafka topic and fill it as soon as CSV files are dumped into this directory. Now, again, we're using Spark, so we have Spark master and a couple of workers. You already see one here. And then finally, we are using the Spark job, which I just showed you. This again depends on the master and the worker. It will still be improved with the health check, so that we are making sure that the Spark master is not only there is not only a running Docker image, but the application inside this Docker image is actually healthy. Now you can read about the pool party graph search more on the below link. What you're seeing here is we are creating basically a faceted search for the financial ratios, which then can be visualized using charts. You can also export the charts as RDF and Spark queries. This is based only on Spark queries, making available the calculated financial ratios. Again, if you have questions, I'd be happy to answer them. If no, I'm giving back to Phil now.
All right, thank you very much indeed, Jürgen. Thank you. I will take control of that then and stick up the general screen there. Okay, so thank you very much indeed. And quite remarkable to have so many presentations and still be more or less on time. We planned to finish at past, so we're slightly running over, but given the amount of content that we've got through, I think we've done remarkably well on that. So time now to turn to the questions, and I'm going to introduce you to Simon Sherry, who is the coordinator of the project along with Zero and Hour. Simon, I think several of the questions here are best answered, or some of them at least are best answered by you. I have questions to ask specific people who've been presenting. There's quite a lot going on here. So first of all, Simon, Theodore asks us whether we're planning to provide an instance of the Big Data Europe Integrator platform that other people can use. Is that going to be on the cloud that other people can use, or if not, how can they use it?
Hi Phil, thanks. It was not planned as one of the objectives of the Big Data platform to provide a cloud-based test service, so to say. We are looking into options still for this because there has been quite a demand, but there was no direct plan to do this in the next months at least. So that's one of the answers.
But people can install it on a cloud service if wanted, yeah? So you can install it on, shouldn't mention it, but Amazon Web Services if you want to.
Yes, and there of course are some free cloud services, but I think the question was whether we can provide cloud infrastructure so that people can test it on our cloud infrastructure, and that we do not do.
You can't do that. Okay, fair enough. Now, I mentioned earlier on that Manuel Mondon from the European Commission has been asking questions about potential use of Copernicus data. Now, we don't have SC7, the SatSen folks, with us today, but they've certainly been using satellite imagery in that. Simon, can you tell us a bit about the pilot around using satellite imagery and detection of change and what's going on there?
So yes, you can find also more information about the 7th pilot, which is the security one on the website. In the pilot section, there's one dedicated just to that. So the idea there is to combine satellite imagery also with social media, tweets in particular, and to identify events happening. There's a nice also example, the example that's usually given to demonstrate this pilot is the earthquake in Italy last year. So you could see there the changes in the surface of the Earth. So when the earthquake took place, and also the tweets and also the news items related to the event, and that was one of the examples. Of course, there's more, so please follow more 7 Societal Challenge pilot updates to get more information about that.
Okay, thank you. And Emmanuel, just to say, if you can completely break all your professionalism and every rule that you signed up to when you joined the Commission, if you can make sure that the follow-up project to this gets funded, then I can tell you that Copernicus data is certainly one of the things that we included in the follow-up proposal, but I know you can't do that. But you raised another question, which I want to actually throw at Jens, and perhaps Luigi and Jürgen as well. You mentioned the issue around taxonomies and how different taxonomies can be used and related ontologies. And we've emphasized during the webinar today that yes, we handle velocity, things like the mobility case from Thessaloniki, and we handle a lot of volume. That's certainly true. But when the variety stuff, there's sort of magically, we turn all this unstructured data into a magic data lake with semantics on top. I wonder, Jens, if you can tell us a bit about how much of that is automated and how much of it is hard work, and how does BDE, yes, we can handle variety, but does the platform actually make it easier to get your head around that variety? How much manual effort is required? And to answer Emmanuel's question there about combining taxonomies, how important are taxonomies and vocabularies in making that work?
Yeah, generally, the Sansa project allows to read in taxonomies and RDF files and work with them. And of course, the Big Data Neural Platform helps to set up all the base for this. So as we heard from Ivan and Hajra, basically this handles all the installation and deployment issues. And then what Sansa is doing is just provides a few libraries on top of Apache Spark and Flink, so we support both projects, and so it's pretty easy to include in projects using the BDE platform and also outside of the BDE platform. In terms of how easy it makes the task, that's a more difficult question to answer. So of course, before you do anything with the data, you have to do the modeling efforts. Here, as far as I understood, there are a lot of taxonomies available already, which could be reused. So once you have those plus your original large-scale data sets, you can read them in using Sansa and perform different analytics tasks. So it really depends on what you want to do. So we have for other domains, we have some things which could work out of the box already, like different clustering algorithms or prediction tasks. Like for remote sensing and Earth observation data, we don't have anything out of the box right away, but it really depends on what you want to achieve in the end. So that's pretty hard to give a generic answer here, let's say.
But it is true.
But yeah, short answer is the Big Data Neural Platform makes it easier to deploy and set up things, and the variety frameworks like Sansa and Ontario make it easier to analyze and query the data.
Understood. Sorry, I didn't mean to try and talk over you. But I think I'm right in saying, and please correct me if I'm wrong, that any kind of ontology that's related to the data does make all that processing easier. And I think I'm right in saying that if there's no ontology, if there's no vocabulary available, then someone has to create it for that data. You do need to know what the structure is. The system is not magic, in other words. It does actually need information.
Yes, yeah. So we cannot do the full magic. So we assume that others have, or let's say domain experts have put in their expertise in creating those ontologies, and the algorithms we develop make use of this. So that's like the distinguishing feature compared to lots of out-of-the-box machine learning algorithms which are not really capable of using the semantics, which just use a plain feature list most of the time at least.
Thank you, Jens. I've got lots of other questions I want to ask, but we're out of time, and I wanted to prod people about performance of the platform and what people think of it, the pilot use cases and so on, and probe a bit more into the outside adopters that Hajira was talking about. One specific question though, again, Theodore was asking us, I don't know, Jens, if you can answer this, or Simon maybe, whether there are specific research papers around the semantic data lake and Ontario. Is there somewhere that people can find out more about that?
Hi, yes, so we published
at the moment,
the paper.
we have this, or...
Okay, no, it's fine. Go on, yeah.
Okay, sorry, I have a slight delay, so you hear my answer a bit later. We have a main BDE research paper, which I also put into the chat box. So that describes big data in Europe in total, and this includes the different semantification components like Ontario, Sansa, and Semacro. So there you can find some information, and the other things are still under review at the moment, so we don't have further material which is public on Ontario specifically.
But I think I'm right in saying that we're hoping to have a paper accepted for ISWIC on this.
Yeah, there's a Sansa paper on for ISWIC and another paper on Ontario, which is also under review. So there could be 2 or more papers in the near future.
We're hoping that Big Data Europe will be featured at ISWIC, which this year is in Vienna in October, so that's something to look forward to. We'll also be at the European Data Forum in Versailles, I think it is? No, Valencia, only BMB, with the BDVA towards the end of the year as well. Okay, I think we're out of time, but I know we're out of time and I'm out of questions, so I think unless somebody else wants to chip in, I'm going to extend thanks to Jens, Hajira, Luigi, Jürgen, Art and Ivan for your presentations today. The recording of this webinar will be made available as soon as I can make it happen. It should be very soon afterwards, as well as all the presentation slide decks that are all going to be available on the Big Data Europe website, and you can see the link there on your screen now. But for now, I want to, again, thank you all very much for coming. Do please fire us more questions by email, whatever, get in touch. We're very open to responding to those. There's a Twitter feed, of course, and goodness knows what. I think I speak with confidence when I say people will be very impressed with the amount of work's gone on here and the enormous possibilities of the Big Data Europe integrated platform. Thank you all.
Thank you. Bye.
Thank you.